Hello, everyone, and welcome back to The Good Stuff. This is the AAS Author Journal Series of the AAS YouTube, and I am tickled pink to have with us today the AAS author, Marina Kounkel. How are you doing today, Marina?
Marina,
sorry.
Very nice to meet you, and thanks for inviting me.
Where are you at?
I am currently at home in Bellingham, near Western Washington University.
Ah, okay. So you guys are shut down? Are you guys closed down?
Yep.
Is there any plans to open up in the fall?
Nothing about the fall. We are closed through the summer so far.
Okay. Nice picture on the background there.
Thanks. I really enjoy Orion, so it seemed appropriate.
Very nice. Did you draw that? Did you paint that?
No, that is actually a 400-hour exposure of Orion.
Very cool. Very nice. And colorized. Very cool. Very good. So what do you like to do for research?
So Orion in particular has been a subject of my study for a very long time.
Okay.
And I have looked at various stellar populations around it.
Okay.
To understand its star forming history and just trying to understand what we can extrapolate from Orion to other populations.
Okay. Very good. And that is a great intro to the start of the paper. So let's go ahead and share that paper with folks. And we are going to cover Untangling the Galaxy 1, Local Structure and Star Formation History of the Milky Way. That's a broad topic. And take it away.
Well, so how it all started is 2 years ago, Gaia DR2 came out, significantly expanding our ability of finding various co-moving groups. And we've sort of classical view of things is when we tend to think about star clusters, we tend to think of something like Pleiades or M80, something that is fairly compact, something that is fairly independent of all the other stars that are around it. But co-moving groups are something that is a bit different. And when we look at the various star-forming regions, including Orion, they tend to be fairly diffuse. They might have some massive clusters inside them, but they're kind of clumpy for the most part.
Okay.
They are huge. They span hundreds of parsecs, and overall not necessarily resemble the clusters as we tend to think of them. So what happens to all these other stars around them? And so with Gaia, we've found that Orion was much bigger than we previously understood to be, that it has much more complex geometry, much more complex star-forming history. And how long would populations like that persist as co-moving groups? Would it be 10 million years, 50, 100? And we can't really answer these questions because with what we know before Gaia, we're just about a dozen or so of co-moving groups within 100 parsecs. In order to find co-moving groups, you need to have velocities. And before Gaia, all we had was Hipparchus, which didn't really have enough resolution and sensitivity to go much beyond 100 parsecs.
Okay.
But now with Gaia, we can go much further. And so I wanted to make Orion even bigger. So there were two stars around it that bothered me. There were Pi 4 and Pi 5 Ori. They are right located in the shield of Orion. And they're around 20 to 30 million years old. They're both B stars.
Okay.
They have very similar velocities. So I thought, well, maybe they are part of a co-moving group that we have previously not found. And so I was kind of scanning the Gaia data by hand still, trying to find something young that is in the area. And I did find something. It was a huge structure extending for approximately 100 parsecs, kind of appearing right around Orion. Now, there were two problems. They had wrong proper motions and they had the wrong age. They were not 20 million years old, they were 70 million years old.
Okay.
Fitted beautifully by isochrone. I still don't know where these two stars come from, but I found something else in the area. And in the process of trying to characterize that particular group, I came across a tail end of another population also nearby. And in trying to chase its tail end, it's quickly expanded to half the galaxy, with dozens of other populations appearing into view. It's kind of like if you're working with a ball of yarn, you pull on one string and everything starts to unraveling.
Yes, yes. Okay.
In order to characterize such a large number of populations, you need to have something that is a bit more automated. You can't just look through data by hand. So there have been a number of various techniques that people have utilized in the last 2 years, trying to cluster together Gaia catalog. And particular algorithm in question that I've used was HDB scan.
Okay.
And the reason why that algorithm is particularly effective is because it is capable of identifying dense clusters and diffuse populations in the same run, which many other clustering algorithms may struggle with. And if you go to figure 1.
Okay. So we're doing that. Let me go back to the 2 stars in Orion that were oddballers, wrong age.
Mm-hmm.
Do you think those are interlopers?
I don't know what they are. I mean,
okay.
They have very similar proportions. People say that some OB stars form in complete isolations. I don't know how realistic that is for them to form so isolated, but there is something else that is going on that I can't quite put my hand on.
Okay, good mystery. Good
yeah.
mystery. All right, figure 1.
Yeah, but when doing clustering, the algorithm makes certain set of assumptions about what is a typical scale of the population that it can find. It's just because an algorithm can cluster something together doesn't necessarily make it a cluster. So to speak.
Not real, right.
Yeah. Depending on what distance you go to, the algorithm assumes particular scales about what is the size of populations in the plane of the sky, what is the typical velocity of dispersion inside them should be. So obviously, if you don't go far enough, you cannot find populations that are too distant. But if you go too far, you might start missing some populations that are way too diffuse.
Right.
So it was necessary to do various slices in distance and then stitch everything together. So as you can see in figure 1, that various runs do kind of recover similar structures, but they might recover it with a different.
So what is EOM and LEAF?
There are 2 different approaches that HDB scan uses. EOM stands for excess of mass.
Okay.
It does a various confusing weighting of how exactly it can separate a particular population from the background.
Okay. And LEAF is then other
Yes.
selections within HDB scan. Where does HDB scan come from? Who?
I don't remember who the authors are. It is based on a much more commonly used DB scan, but it just the way it operates is slightly. It's just the way it normally things is slightly different.
Okay, note to self. Fine then. Okay, very good.
But it has implementations in both Python and R and other languages.
Okay, and so got it. So the left is south and the right is north. Is that?
Yeah, so the left is actually Orion and the right is Ophiuchus and Corona Australis.
Right. Okay.
And
got it. So which of these grouping algorithms do you trust?
Well, I mean, all of them work in their own
domain,
in their own set of conditions. So we've ran a whole bunch of them, kind of slicing it up like an onion, and then stick everything together.
Got it.
Because everything is identifying some structures, it just at slightly different sensitivities.
Cool.
So in total, we have clustered together approximately 300,000 stars in approximately 2,000 different groups.
Wow.
And if you scroll to figure 2.
Okay. Ooh, like this one.
So we went up to a kiloparsecond distance, and we've limited ourselves to within 30 degrees of the galactic plane, because that's where the plane of the galaxy mostly is. And that's where we can mostly ignore the non-linear effects of the galactic latitude. So in blue are all of the 300,000 stars that we have clustered together. And in contrast, in yellow are most of the previously known open clusters in the same volume of sky. And as you can see in terms of spatial coverage, they are very, very different. So we tend to think of clusters as these compact things that you have to specifically hunt for these populations in order to find them. But what we're finding is that these stars that are in these extended populations are everywhere.
Wow.
And the convenient thing about finding co-moving groups is presumably all the stars inside them formed at the same time, give or take a few million years. So it's possible to determine their ages with isochrons, so isochron fitting. And actually doing isochron fitting for thousands of different populations is a non-trivial task, unfortunately. So for something as fundamental as isochron fitting is something that we have taught since the very first introductory classes. There are surprisingly few algorithms that are actually able to do it robustly. So we've tried a few various things. We've tried neural networks, tried to extrapolate ages from the photometry. We've tried an algorithm called Base9, which actually does fitting, but it does require having some initial estimates for the population ages of the population should be. And then we've looked through all of these ages by hand, kind of trying to fine tune things, and it wasn't pleasant. So in the paper 2 that we've recently submitted, we've advanced the neural networks that it works on everything. But so far, if you can scroll down to the next set of figures. Yeah. At least in this paper, the ages were still kind of a mixed bag of where they came from. And you can see in figure 4 that you can see how the progression of the young populations of less than 1 million years old to approximately 100 million year old. You can see that how the pre-mate sequence shrinks down, and then how the turn-off evolves for populations older than 100 million years old. And so figure 5 shows the total histogram distribution of all ages of all the stars. So we were actually able to find all of these, to estimate ages for incredibly large sample, much larger than probably any other work before.
Okay, so two things, one for everybody. This paper is a little unusual and has a lot of interactive figures to it, and you can kind of get a sense from that in figure 4. There's a slider bar there in the PDF, which of course won't slide, but we're going to be taking a look at a couple of those interactives here in a second. Okay, I'm good with, so, no, I'm good with that. I get it. And just for clarity, that age in figure 5 on that, that's, so 8 would be 100 million years, 10 to the 8th. Okay, I'm good. So the young and the very old. Okay, I'm good.
Yeah, and so I think we can go to figure the interactive figure that we were talking about.
You want to go to the interactive?
Yep, to figure 8.
Okay, I'm going to stop screen share here for a second, people, and I'm going to do a screen share. This will be an experiment, everyone, of the interactive figure.
Yeah. If you were to change the age slider from 7 to 7.5.
So what's on each of these? There's 5. Okay, so the bottom is radial velocity.
Yes. So here we have L, galactic longitude versus galactic latitude, parallax, proper motion in L, proper motion in B, and radial velocity.
Okay. And so this thing is a slicer. So if I just cut out all the
so right now you just remove all the young stars. So let's just look at the younger ones.
There's very old ones. Okay. So if we want to then just look at the young ones, we slide it from the bottom, and let's say 7.5, and those are the new ones.
Yeah.
Or the younger ones, we should say.
Yeah. So I did mention that it all started with trying to trying to chase a tail end of one of the population, which was very long. It's covered, well, not quite half the galaxy, but a very large portion of it. And it was long and very filamentary. If we were to look at all of these very young population, you can see that most of them are very long and very filamentary, kind of string-like.
Yeah.
So
Mouse over.
yeah. And so yeah, you can switch between these very compact groups that kind of exist outside of everything else and these long strings of stars. And at the youngest ages, almost everything is part of a string with very few compact structures.
Yes, very much. Yeah. Okay. Yeah.
Well, at these ages, it would be impossible for them to be tidally stretched to these dimensions.
Okay, so strings here, when you say strings, I thought that was maybe character strings. Strings here refers to the elongated open groups.
Structures, yep. So it will be impossible for these strings to be formed through the tidal stretching of previously compact open clusters.
Okay.
Rather, it's very likely that they are primordial. We know that stars form in giant matter clouds. Clouds themselves are filamentary. Anywhere you have a high density of gas, you're going to start forming stars. So it stands to reason that the stars are going to form all along a filamentary cloud, and they will still kind of retain that overall morphology for a considerable length of time before they start kind of diffusing into the rest of the galaxy. Yes.
I'm having too much fun.
That's opacity controls.
I'm learning something about the galaxy. Isn't that cool? Yeah. All right.
And so these strings are ubiquitous at the ages of approximately from up to ages of 100 million years, but after 100 million years.
Okay.
Something at, if we're to look at, if we're to look at from 8 to 9, let's say. Yeah. So now you still have some of these strings, but they are starting to get a bit more diffuse, and there are fewer of them. You slowly start to accumulate more of the cluster-like, more isolated groups. So it's likely that these groups were still originally part of these long strings, but all the diffuse material around them has already dissipated into the galaxy, dissolved into the galaxy. And by the ages of over 1 billion years, or greater than 9, then you still have a few of these strings, but almost all of them are in groups.
Yep. Very cool.
Yeah, so this kind of shows us that probably some of these most massive strings, something like the size of Orion, something that contained hundreds of thousands of stars, would have been able to persist for such long ages. And right now, they contain only a few dozen stars, so they're not massive at all. But you still can find just a few stars that are still being held together, kind of still appear to be co-moving.
Okay.
Yeah.
You want to go back to the article, or?
No, let's go back to the next figure, the next interactive figure.
The interactive?
Yep.
Okay.
Yeah. So this is a fun figure. This is trying to place all of these populations in the heliocentric reference frame, with the sun being at the center, and the center is to the right of the image. And all of these strings are being traced along their spine as a line. And all of the compact groups are represented as dots. And we can do the same thing. We can look at different age ranges.
Very nice.
Yeah, and as you can see in this very young age slice, is that their arrangement is not entirely random.
No.
If you look at them face on.
Face on, let's go face on.
Yeah, So there are many of them kind of located along x of 0, very few at x of plus or minus 1,000. And this is kind of where the spiral arm goes, the local spiral arm goes up and down almost. And all of these strings are oriented more or less perpendicular to it, with some scatter, of course, but roughly perpendicular to it.
Let's take a look at age.
But now, now that we're looking at the different age slice, 100 to approximately 300 million years, you see that the overall orientation is slightly different.
Yeah.
So before they were kind of going almost up or maybe a bit curving towards the upper right. Now they're curving a bit to the upper left. And if you go to the 9 to 9.5, you can see that it looks entirely different, that there is one population kind of on the top of the image, kind of going diagonally, and there's another one that is going in parallel to the one at the bottom left, bottom right, the other one is at top left.
Okay.
With very few of these old strings located near the galactic circle.
Right.
So if at the youngest ages, these strings are tracers of the spiral arms, well, perhaps at the older ages, we are tracing the spiral arms as they existed back then. They are no longer associated with gas, but they're still kind of preserving the same underlying morphology that they have originally formed with. So this kind of shows us the timescales for the spiral arms twisting and turning and disrupting and reforming and snapping back again. So we've been kind of trying to work with few modelers looking at few simulations, and we can actually find that the signatures of spiral arms do persist for well over 1 billion years.
Okay. Yeah. Very nice.
Yeah, thanks.
Very nice.
And so the V plus shows the velocity vectors. We can remove the velocity vectors entirely.
Got it.
Those fuzzy lines.
Yeah. Oh, nothing there on that age. All right. Really? Okay. So if we go young and strings are off, okay, I have to ponder that. How about older? No, older wouldn't get it at all because what we saw earlier.
Well, if you're turning everything off, you need to turn something on.
Oh, yes, that would be useful, wouldn't it? I was trying to get the, there we go. That's what I was trying to get at. Okay. Wow. A lot of exploration one can do in here.
That's why I've wanted to make it interactive plots, because I've spent half a year looking at various projections of these data sets, and I couldn't pick just one.
What software did you use to do these?
This is done using Plotly.
Okay.
It's a JavaScript library that has extensions in Python. And another fun thing you can look at here, if you look at the edge on.
Edge on X.
Yeah. And you can scroll through different ages just to see how the scale of the galactic disk changes across different ages.
Oh, you meant we want to change the scale here?
Yeah.
Okay. There's young. Okay. Let's go middle and 100 million range.
Yeah, you can see how it starts to puff up.
Yeah. And gets a little bit more, there's more coverage of it as well. And then we'll go, quote, old. Ooh, definitely puffs up. Yeah. Heating of various forms. Disk puff. Very nice. And in fact, you should be able to see that if you do, well, okay, a little harder to see. But yeah, you can even on this plot see there's puffing up as the color becomes bluer.
Definitely, yes.
Yeah, but it's clear if you use the slider. All right, anything else you want to show here?
Not in these figures, no.
Okay. So we will go back to the paper if you like. The article, I should say.
So if we go to, I think, figure 9.
Figure 9. Figure 9.
Yes, so this kind of shows the apparent dimensions of all these various strings. That you can see that the strings have, well, you could see it clearly on the images themselves, but this is kind of a more numerical sense of things, that they are much longer than they are wide. They're wide. They have very high access ratio. And that their apparent width doesn't really change much with age. But, even at the older stages, even though they don't necessarily have many stars, they are also pretty long. If you look at figure 11.
Oh. Okay. Figure 11. Okay. Age is by number count here.
Yes. So at the youngest ages, you can start with pretty much whatever number of stars in your population that you like. You can have a few hundred stars, you can have several thousands of stars, but by the oldest ages, it's rare for them to have more than a few dozen stars. Just because, they, as I mentioned before, they are starting to evaporate into the galaxy.
Right, right.
Recovering just a small still moving population.
Mm-hmm.
And I guess we can end with figure 14, kind of the bottom edge.
Hey, that looks like some things we're looking at there.
Yep.
Ooh. Okay, figure 14. Let's decrease that a little bit to get the full figure on there. There we go.
So the top shows just various correlations between the position and velocity. Not terribly interesting, but the bottom part of it shows, well, we've already looked how the scale height of in Z increases as a function of age.
Mm-hmm.
And it increases even further if you were to look at completely unclustered field stars. But also if you were to look at all the various velocity components in UVW, so those are galactic vectors, they are also increasing in velocity dispersion as a function of age.
Why do we have a U and a U corrected? What is it?
So there is, because of the rotation, you have a bit of a shear. You can see it kind of on the projection of Y versus U. It's not flat, it's more of a diagonal. So just to remove that rotation effect, it shows a very similar thing, but it's a bit cleaner, I think. So yeah, these populations are evolving dynamically. At the youngest ages, there is a bit of a galactic warp. That's why it's not a complete increase from 7 to 8 million dec, or from 10 to 100 million years. But you can still see how they are evolving dynamically. And so this set of population kind of allows us to answer questions about stars and star population across all different scales. You can see how stars evolve because we now have a large sample of stars with known ages. We can see how stellar populations are evolving because we are actually seeing how different slices work at different ages. And we are seeing how the galaxy is evolving because we can place them into the galactic reference frame.
Yes. I have one question on the figure 14 here.
Mm-hmm.
Another question. The dots there represent field stars?
No, I think if I remember correctly, this should be individual dots represent different groups.
No, so in the bottom part of figure 14, where you got the velocity scatter and the z scatter,
yes,
you've got circles.
Yes. So that's average. If you were to take all the stars that are not clustered, most of them are likely to be even older than what we can recover.
Got it. Okay. Very good. Okay, cool. So you mentioned going forward. So that was paper one. You mentioned that you submitted number 2.
Mhm.
Is there a 3, a 4, a 5? Where does the field go given this spectacularly nice job you've done with the Gaia data?
Yeah, so in the paper 2, we went up to 3 kiloparsecs, kind of to the limits of what Gaia data permits. And we also did a slightly nicer job of deriving ages using a neural network.
Okay.
And in that paper, we have a catalog of approximately 8,000 populations. And we're actually going far enough to cover nearby spiral arms, such as Sagittarius and Perseus arm. I apologize for the noise outside. So some of the other things that we're interested in is here we are able to find stars that are clustered, but there are other ways of finding young stars, just from looking at the HR diagram. So working together with some students, we are trying to derive a set of various criteria that allow us to just select all the young stars, whether they are clustered or unclustered, and just compare two different samples to actually directly see how these young stars are leaving their nest sites. We are working with a few modelers, trying to connect the observational perspective to the modeling perspective, just to see how exactly these spiral arms are evolving, how exactly these populations within these spiral arms are evolving.
This gives a pretty rich data set
Yeah.
To constrain or compare against. So it's very nice.
Yeah, yes, specifically looking through time, not just as a snapshot of galaxies. But
So so I'm curious. So then once you've completely mined Gaia DR2, what's the next step observationally? Do you have to wait for a super Gaia or something like that? Where do we go observationally? What would be the next step? And you can go out, however far you need to go out, 10 years, 20 years, whatever it is.
well, the thing that I'm quite excited about is SDSS 5.
Okay.
Because Gaia gives us proper motions,
Yes.
but we also need radial velocities. Gaia does measure radial velocities, but they are not quite as good as we can get, and not for as many stars as we can get. So next generation surveys such as SDSS 5 with Apogee will give us a more uniform radial velocity coverage of the galaxy, which will definitely help constrain some of the other things in the sample, because we can try to extrapolate what is the radial velocity component in some of these plots, but without accurate measurements, that's only an estimate. Gaia DR3, whenever that comes around, they have delayed it a bit recently. That will give us a lot of information on stellar multiplicity. And multiplicity is one of the topics that has been that I've been fighting with for many years, because you cannot study stellar dynamics without worrying about binaries.
Yep.
Cool. And one of the interesting things that if we were to look at binaries around very young stars and around binaries in field stars, there's a slight mismatch that there are more binaries in young stars at particular separations where they are unlikely to be disrupted dynamically. So we don't know what is the difference between these different binaries, and looking at how multiplicity evolves as a function of age would also be quite interesting.
Yeah, very nice.
So there are many different perspectives from where this could go in the future. Just trying to figure out what is the highest priority is a bit of a challenge, actually.
Right. Yes. So the future is bright. a lot of potential, a lot of potential directions. That's awesome. Well, Marina, thank you so much for taking some time this afternoon and walking us through your spectacular paper one. Yeah, for those of you who would like to talk with her more, you know how to get in touch with her by email. We won't be putting her email address in the YouTube video or in the description. but you'll know how to get her if you're in the game. All right. Thank you, everyone, so much for listening, and we'll see you on the next one.
Nice talking to you. Thank you.
Thank
Bye.
you. Bye-bye.